I've talked a great deal about what is good and what is better, and we're now going to apply that to decision analysis and normative analysis of how what should be done, what the targets of environmental policy should be. I'm going to talk mostly about cost-benefit analysis, but I'm going to talk about some alternatives as well. This is where we are in the sequence, and I'm going to start by talking about efficient flow pollution after a short introduction. Robert Solow wrote that economists have a reputation of being unimaginative bean counters, doggedly claiming to quantify the unquantifiable, and personifying Oscar Wilde's definition of a cynic as someone who knows the price of everything and the value of nothing. It is true that they, economists, would give a lot for a rough quantitative answer, but it only reflects the fact that any policy can be pushed harder or less hard, further or less far, and that a useful evaluation has to suggest how hard and how far the beans have to be counted if only approximately those gentle souls who nearly ooh and ah over them are arguably part of the problem, not part of the solution. And this is what cost-benefit analysis is about. The decision how hard or how far to push a policy. Abraham Lincoln said something similar. The true rule in determining to embrace or reject anything is not whether it have any evil in it, but whether it have more evil than of good. It is about making trade-offs. That's what cost-benefit analysis is about. Johan Cruyff said it most succinctly, that every upside has its downside. And that is what cost-benefit analysis is about. Trading off the upsides against the downsides, and not pretending that things only have upsides or only have downsides. We do this in the context of environmental pollution. Just a reminder that pollution is an externality. It's the unintended consequence of someone's production or consumption on somebody else's production or consumption. And because it's an externality, these things typically do not happen in the same place. Typically, factory emits some contaminant, and then the wind takes it elsewhere, and there it does damage, or it is thrown in the river and transported in the river. So environmental transport is important in sort of connecting the source to the impact. And all sorts of things can happen. The contaminant can be absorbed by some plant or animal and then does no harm to humans anymore. It can respond to other chemicals that are in the environment, and that can make it worse or can neutralize the original emission. And all these things are important. The impact of pollution also depends on the existing pollution that is in the atmosphere, in the waters, or in the soils. And in some cases, just a little bit of pollution can do a lot of harm if it falls in a pristine environment, but then if you emit more and more and more, the damage is basically done, and emitting more does not do additional damage. But it can also be the other way around, that the initial concentrations of your pollutant are actually harmless, but it's only when you cross certain thresholds that damage is done. I'm not going to talk much about these things, but it's important to keep that in mind, that we actually need to reflect the physical, chemical, and biological realities of environmental pollution. I am going to talk about flow pollution and stock pollution, and obviously there's mixed forms as well. Noise is the canonical example of flow pollution. That is, as soon as the activity stops, the pollution is gone. If I get up at 5 in the morning, I start my engine and wake up the neighbors. That annoys them quite a bit, but as soon as my car leaves the street, the noise is gone. Right? That's a flow pollution. The canonical example of a stock pollutant is nuclear waste. Some of that stuff, some of the nuclear isotopes have half-lives of tens of thousands of years. And that means that the activities of today will still have consequences 10,000 years in the future. And that is a canonical example of stock pollutants. And the more chemical and nuclear waste you have, the bigger the problem. It accumulates over time. As I said, I'm going to start with analyzing flow pollution. Now, what would be the optimal level of pollution. Let's assume that the damages of pollution are denoted by D, and that is a function of emissions M, and this is just a function, can be anything. The benefits of the polluting activity, what did I do? Are denoted by B, and they're also a function of emissions M. And if there were no benefits of the polluting activity, then of course you would never do it, right? Then you would never generate this externality. The net benefits are therefore B minus D, and we want to maximize the net benefits. That's what cost-benefit analysis is all about, by maximizing the net benefit. And in order to do so, what we need to do is an unconstrained optimization problem. So we need to set the first partial derivative equal to 0. The first partial derivative, that is to the choice that we're making, that is how much to pollute. So that's dn b at dm, first partial derivative of net benefits to pollution, should equal 0. That is dB dm minus dt dm should equal 0. Or this is the usual form in which you see it. The marginal benefits should equal the marginal damages. That is how much flow pollution you would like, or that is the condition to derive that. So that's algebraically. Let's do this graphically. So what you're looking at here in this graph is on the horizontal axis you have emissions, on the vertical axis we have the gain, and then here we have some curve that describes the total private gains from emissions. And if you have no activity, you have no emissions, but you also don't gain anything. You do more and more and more of it, and at a certain point it becomes too costly, or you've had enough, and your benefits are beginning, your private benefits are beginning to fall, and at that point is where you stop. This is the highest point on the total. There we go. There. This is the highest point on the total curve, and that is of course found where the marginal curve, first partial derivative, or the slope of this curve equals 0. That is Q prime is what you would do if unregulated. So this is the side of the polluter. Now there's also damages from this pollution, and that curve is given in green. If there's no emissions, then there's also no impact of those emissions, we assume, and the higher the emission, the worse it gets, and that actually accelerates for higher emissions. And then we can draw the net gain, that is the benefits of the pollution minus the cost of pollution, and the result is this red line. And what we want is to maximize this, that is to find its highest point. And you do so by equating the marginal private gains from emissions, that is the brown dotted line that we saw before. This green dotted line are the marginal social losses from these emissions. And in the algebra you saw that there was a minus sign popping up, so that is why this is now increasing. And essentially what this says is that there's no emissions, there's hardly any losses, and a little bit of additional emissions does actually very little damage, so we don't care much about that. But the worse it gets, the higher the emissions get, the worse we think about this, right? And this line is increasing, and then the optimum point is where marginal gains and marginal damages meet, and that is by construction the same as where the marginal net social gains equal 0, right? Because this red line is just the brown line minus the green line, right? So where these two meet, the red line, the dotted red line, goes through 0. So that is your optimal point. We can and that is the optimal amount of emissions that we want to allow. We can talk a little bit more about this graph, talk about the areas that are in there, just to make everything a little bit clearer what this all denotes. So the area B this is the area under the curve from 0 to the optimal point. That's the area B. That is the optimal amount of pollution. This is how much of the externality we would allow. And if we add A to it, we have the optimal amount of the producer gain, of the producer surplus, I should say, of the emitter, right? This is the amount of polluting activity for the welfare gained from the amount of polluting activity that is allowed, right? And this upsets people sometimes, right? That the optimal level of pollution is positive, and the polluter should actually gain something, but this just follows from maximizing the net social benefits. And that is maximized because this area A is positive, right? So this is the gains from the polluting activity minus the losses from the pollution, and this is the net social gain. That is what A means. And that is what we're interested in. We're not interested in minimizing pollution, we're interested in maximizing net social gain. The area here is the total damage of pollution that we avoid by optimal regulation. By pushing the quantity of emissions from Q prime to Q star, we avoid this amount of environmental damage. So it's not that the cost-benefit analysis ignores the environmental pollution. No, not at all. It actually cuts it quite a bit from this area down to this area, right? So there's a good bit of environmental gain there. It's also that the polluters don't come off scot-free because they would rather do this, but then if we cut it down to the socially optimal level, we go from Q prime to Q star, and that means that this bit of producer surplus of the pollution is unwarranted and should be taken away. Right? So there's actually quite a bit of action going on in this particular figure. The key point here is that the optimal pollution, Q star, is much smaller than the unregulated amount of pollution, but it's also much larger than 0. And that is because the laws of thermodynamics essentially apply that you can do basically nothing without generating at least waste and typically also pollution. And you may argue that this comes because I assume that there are no thresholds in the system, right? I assume that there is no assimilative capacity of the environment whatsoever that is the minimum amount of pollution actually does no damage at all. So what happens if we have a assimilative capacity in this figure? Well, then essentially what you say is that instead of having the dark green line, we have the light green line. That is, if the first bit of emissions sort of gets absorbed by nature without doing any damage, then the initial emissions actually have 0 negative consequences, and it actually starts later that they are beginning to have environmental negative consequences. And that means that the dark green line becomes a light green line. You actually shift down, and that means that the optimum that was here actually shifts to the right, and with assimilative capacity you will actually allow for more emissions. The optimal amount of emissions is larger, not smaller. That is the take-home message here, that optimal pollution is not only greater than zero, it's also greater than the assimilative capacity. If we're interested in maximizing the net social gain, then we would allow some pollution. And this follows from the fact that the polluting activity is valuable as well.